Yes, in this video, I want to talk to you about the axioms of probability theory. One possible approach to the topic of probability is to first define what properties a probability measure must essentially have in order to meaningfully delve into probabilities. This does not fully define what it should be, but it actually helps to derive properties that we can infer from the axioms. And that is what we want to do. So I will first tell you what the axioms are, and then we will look at some consequences of these axioms. All right, so we will start here with this definition. First, let's cover some general information. On one hand, we need a random experiment. We have an event, A, and a sample space, omega, which is essentially what we have defined beforehand. And a probability is now something that we assign to an event. And then we write P of A as it is pronounced, and we write P in parentheses, A, and A is an event, so a probability is something that we can assign to each event. And this must fulfill the following rules or axioms. This definition. The first axiom is that the probability of A should lie between 0 and 1. Yes, you can say 0 and 100%, or you can express it as a value between 0 and 1. We will often not calculate with percentages here, but with decimal numbers. And that should be clear to them. There are no negative probabilities, and there are no probabilities that are greater than so far so good. The second axiom is that there is a certain event, which is omega. This is the event that always occurs, and it is supposed to have a probability of 1. So, this is essentially established. By the way, we will see that it follows from the axioms that the empty set, which is the impossible event, has a probability of 0. We don't even need to demand this separately. Rather, we will see that it actually follows from the axioms. And the third axiom is the so-called addition rule. The addition rule states how we can, when we have two events, namely events A and B, and it is important that they are mutually exclusive. Do you still remember what mutually exclusive meant? If not, just a quick recap. This essentially means that A intersected with B is the empty set. Yes, both cannot occur simultaneously. For example, the even numbers and the odd numbers, A is the set of even numbers and B is the set of odd numbers. And the nice thing is, when we have two events like this, we can easily choose the probability for their union, namely as the sum of the two probabilities, provided that the two are mutually exclusive. And it is clear that this only applies to mutually exclusive events. You can easily construct an example for yourself where this is not the case. And we can briefly think about it again. How would that be now? So if we take A as the even numbers of a die and B as the odd numbers of a die, then they are mutually exclusive. And the total set, that is, the union of A and B, would be the entire sample space. And that makes sense. That would be a probability of 1, and well, the probability that it is even is 1/2. The probability that it is odd is 1/2 as well, so 1/2 plus 1/2 equals 1. So you see, in this example, it all works. And now you may be wondering, why did we choose exactly these three rules? There are many more. For example, I have already mentioned that the probability of the empty set is 0. What about the probability of the complementary event? Such things And the nice thing now is that all important properties logically follow from these three axioms. And I want to show you a few conclusions right now, and at least one of them we will also demonstrate. Now let's look at this conclusion. The probability of the complementary event is 1 minus the probability of A. And I want to try to comprehend together with all of you why this follows from the axioms. Think about that for a moment and let's look back again. So, these are the axioms. We somehow see that axiom 2 plays a role here because the number 1 appears somehow. And perhaps we can also use axiom 3 in some way. Alright, let me show you. We can write omega, which is the trick, as A united with not A, right? So the set of all possible outcomes is either A or the complement event not A, and at the same time we know that A intersected with not A is the empty set. This is exactly how they are constructed. Well, and now we can know on one hand that from axiom 1 I will write it like this, that P of omega equals 1. And from axiom 2 we know that we can write P of omega as P of A plus P of a prime, and that was equal to the first. And then we actually have it almost done. Now we simply share an image. We subtract minus P from A, and we get that P of A is equal to 1 minus P of A. And with that, we have drawn this conclusion here. Yes, one must come up with this trick of writing it all out this way, and then one can use axiom 1 and axiom 2. What else is there? There is also an addition rule for compatible events, meaning not only for mutually exclusive events, but also for those that are compatible. This looks as follows. So we have a union B. What we then do is calculate P of A. But we have added a bit too much. Namely, we have effectively added the intersection twice. So we need to subtract it once more. And in this way, we also obtain a formula for the probability of a union B. You can also just consider this idea. You can let your mind wander on how you can prove it. Perhaps we can go through it again. I'll continue. And another conclusion is that this can be generalized even further. Axiom 3 can thus be applied to even more events, provided that each pair of events must always be mutually exclusive. Exactly, that means that each individual event has the empty intersection. And perhaps also an interesting question 4, namely monotonicity. So, if A is a subset of B, then it also holds that the probability of A is less than the probability of B. This can also be demonstrated from the axioms. Can you also think about how you can do that? Specifically, which axioms you might need for it? Well, those were the axioms of probability theory, and in the next part, we will take probability theory a step further and deal with the so-called conditional probability. Until then.